Good morning, everyone. Thank you for being here. My name is Yicheng Guo. I'm coming from the University of Missouri, Columbia. So first, I'd like to thank the organizing committee for giving me this opportunity to share my work with all of you. To be honest, that before this week, the majority of my knowledge of Roman was coming from reading NASA's websites and fact sheets from NASA and STSCI. By the way, they are very helpful. So this week is also a good opportunity for me to catch up with the community to learn the status of Roman. And again, I'd like to thank the organizing committee, Takahiro and Lee, for running this wonderful conference. Okay. Today I'm going to talk about low mass galaxies at intermediate redshifts. So I didn't do too much with Roman, so please take it as like a community input for Roman project. So trying to make sure it's working. Looks like the turning page is frozen. Yeah, it's frozen. Okay, click again. Okay, great. Thank you. So low mass here, I mean stellar mass from 10 to 8 to 10 to 9.5. And intermediate redshift, I mean redshift 0.5 to 1. We can push it to redshift 2. And you may argue whether those are low redshift or intermediate redshift. So just keep in mind the age of the universe is about 6-7 billion years at redshift 1. It's half of the current age of the universe. So let's call it intermediate. Okay, so those are my collaborators. I have some long-term collaborators, Sandy Faber, David Koo, and Guillermo from Kendall's team, which is the WFIC3 large survey. And also I have some collaborators from Hello 7D. This is a deep CAC DEMOS survey. And I also have some collaborators, John and team. They are my former postdoc, and TJ are my current graduate student. So you may ask, why should we care about low mass galaxies, especially that mass range? So usually I have 4 answers. From most straightforward to the most physical. So first, the majority of galaxies in the universe is low mass galaxies because the stellar mass function increases as a power law towards the low mass end. So if you integrate the number of galaxies between 10 to 8 and 10 to 9.5, 75%, 80% of galaxies in the universe are actually low mass galaxies. So that's number. Second, we all care about the formation and evolution of our home galaxy, the Milky Way. So if you push Milky Way back to early universe, it was a low mass galaxy. So that's why understanding the formation of low mass galaxy is important to understand our own galaxy Milky Way. Okay, the third one is the example here. So low mass galaxies, they are very strong test on the physics of baryons. So here is an example. If you look at the metallicity versus stellar mass around redshift 1. And the red one is the data from my paper 2016. And the blue curves are 3 different models of feedback. So here feedback means any kinds of momentum or energy that are dumped by supernova or AGN to the interstellar medium to heat up or to expel gas out of galaxies. So the top blue curve is what we call the preventive feedback. Basically, that means gas got heat up before it falling into dark matter halo. And the middle one is the normal ejective feedback. You have feedback from a supernova and it blows away gas. And the bottom one is called the re-infalling feedback. So you have ejective feedback and you allow the gas to re-falling into the galaxy. So the prediction from 3 different models, they kind of converge at the massive end, but they diverge dramatically at the low mass end. So if you want to test what is the model of feedback, what is the real mechanism of feedback in galaxies, low mass galaxy would be the best test bed. And the last but not the least, actually the most important in fact, is low mass galaxies are also a good test bed of fundamental physics, the connection between baryons and dark matter particles. So here is a plot from the annual review of James Bullock and Michael Bolan-Cochin, 2017. So this is a famous COSPO and core problem in cold dark matter. Okay, so this band is the prediction from NFW. Basically, alpha is the slope of dark matter halo. So the lower value means the steeper the slope, and the higher value alpha means the flatter the slope. Okay. So the purple band I still need to get used to this. The purple band is a collection from observations. As you can see, the observations, since there's a core, which means the inner slope is flatter, but the NFW model, the n-body simulation says the inner slope is very steep. And the biggest difference actually coming from those we call the bright dwarf galaxies. And this is the mass range I'm talking about today. Okay, so this is a very outstanding problem in cold dark matter theory. And there are some solutions. One of the solutions is to involve baryonic physics, because n-body simulations, you only have dark matter. So if you include the baryons, and especially if you include feedback from starburst, and those feedbacks, if they happen very rapidly and repeatedly, so they can heat up the gas in the core of galaxies and to expand the core, and because of interaction with between the gas, baryons, and the dark matter, the COSP of dark matter could also be dumped to form a core. And this is very commonly used solution for the COSP and the core problem. And as you can see, those scattered data points, they are from numerical simulations involved baryonic physics. Okay. So here I have, I hope it's working, simulation from fire, feedback in realistic environment. And this is the formation history of a low mass galaxy. I want to show you what is the starburst and the strong feedback I said that people used to explain the COSP and the core problem. So green means warm gas, hot means, red means hot gas, and purple means, I think it's neutral gas. So you can see around the redshift 1.5, there's a very big burst, almost blow away all the gas in the center, and another one so there's a small burst from time to time, and there's another one around redshift 1.1. You can see almost all the green gas got swept out. And I think there's another one around 0.5. Yeah, you can see gas got blown away by supernova feedback. Okay, I'm going to stop here. So this is the star formation history of the same galaxy from fire I just showed you, and you can see it's not smooth. It got up and down, up and down. And to explain the COSP and the core problem, the period of a burst should be matching the time scale, dynamic time scale, in the inner part of dark matter halo, which is about 20 to 50 million years. So that means you need a burst with a duration or period of tens of million years. Okay, so last time when I show my talk to some theorists, they say, okay, problem solved, right? It's a starburst. I say, wait a second, okay. It was solved in your simulation, but is that true for the universe? So that comes to my first part. Okay, to test whether low mass galaxies are really or observationally burst in the universe. If it's bursty, that's fine. We can take the solution of Cospo core problem. If it's not, then we probably have to consider other solutions. For example, change the nature of dark matter to use warm dark matter, fuzzy dark matter, or self-interacting dark matter. Okay. How should we test the burstiness of low mass galaxies? We can use basically two different star formation indicators. One is from nebula emission line, because nebula emission line is driven by O star, and it can trace star formation rate at a 10 million year time scale. Or we can use far UV. Far UV is driven by O star and B star, so it traces star formation rate at a time scale of 100 million years. Here, if you have a single burst, and if you look at the trend of far UV here, red, and also H alpha nebula emission line, and you take the ratio of H alpha over far UV, you can see right after the burst, and the H alpha is way fainter than far UV. And if you imagine you have this burst from time to time, and when you sample the time range, you actually have more chances to sample this part where H alpha is fainter than far UV. So as a result, here is another model from VHAM Meta 2023. So for different burst time scale, if you have burst of a few million years, and if you look at the sample of low mass galaxies, their medium H beta or H alpha to far UV ratio would be less than 1. Here I say ratio, I use star formation rate to normalize them. So on the other hand, if the star formation history is flat, and if you look at the sample of smooth galaxies, their H beta to far UV or H alpha to far UV ratio would be close to 1. Okay. So this is the method we are going to use to test the burstiness. And here is a result from my paper 2016. And we didn't use H alpha, we used H beta, but it's the same story. So H beta over far UV, and this is a stellar mass. Well, lots of scatters, so that's why we need a Raman to get a much larger data sample and to reduce the scatters and improve the statistics. So if you look at the red squares, so they are the medium ratio of H beta to FUV, and they decrease with the stellar mass. Okay, again, lower ratio means bursty, and close to 1 means non-bursty. Okay, so this is consistent with low mass galaxies are bursty around redshift 1. Now you said, okay, you just showed me the wonderful simulation from a fire, and you showed the very bursty star formation history of simulated galaxies. Can we do a comparison with the simulation? And here is the H alpha over FUV ratio from a fire, and the black band is from local universe, and the gray arrow bars on the curve is from a fire simulation. And our result from candles and Hello 7D matches the prediction of fire very well. Okay, so that tells us, okay, we find a way to test whether low mass galaxies are bursty or not. And our preliminary results shows they are indeed bursty. So we go one step further to say, okay, can we set up some simple models of star formation history? For example, the change of star formation history. So we know the period, which is the time between the two bursts, and also duration of each burst, and also the amplitude of each burst compared to a continuum star formation history. And then we can calculate a parameter which we call the burstiness, which is basically d duration times amplitude divided by p, following the model of Dunn-Whistle et al. 2012. And the meaning of the burstiness is basically how many stars were formed in the bursty phase over how many stars were formed in the smooth phase. Okay. If you look at the local galaxy, which is the blue curve here, and if you compare all results at redshift 0.5 to 1, so you can see higher redshift galaxies are more bursty than local galaxies, and also the burstiness increase when you go to lower and lower stellar mass. Okay. So after 2016, 2017, there are many other papers to point to the same or similar results from, for example, Brian Siano's group, led by Amami et al. 2019 at redshift 0. Attack 2012 used the GRISMA data from HST, find similar results at redshift 1. And Forceta et al. At redshift 4, again, galaxy become more and more bursty when you go to higher and higher redshifts. And overall, we find like bursty phase, they formed about 2 or 3 times more stars than galaxies in the smooth or continuous star formation phase. Okay, this is good, but we have to be very careful about lots of systematics. If you look at the paper of Rizzo et al. 2023, so we have to worry about IMF, dust extinction, even binary star evolutions, so far and so far, and also we have to worry about sample size. Because in my sample, we only have like 160 galaxies, and we really need to enlarge the sample size. And Roman, by providing broadband photometry and also GRISMA, can enable us to push such study to higher and higher redshifts. Okay, here is a quick summary of the part of burstiness. Low mass galaxies are bursty, and I didn't have time to talk about the study from my graduate student, Tija Tipala, recently. Basically, we find the bursty width duration is 10 to 20 million years, and the period is about 40 million years. So here are 2 implications. First is a scatter of the star-forming main sequence because of this bursty phase would be increased as stellar mass decrease. And again, this is something Roman can help us to test by providing GRISMA and to a larger sample. And the second implication, maybe a little bit stretched, is low mass galaxies, they are unlikely to stop their star formation by themselves just through starburst or supernova feedback. Because you can see feedback, but you can see also refalling of new gas. Okay. So the second implication is actually connected to the second part of my talk. What is the quenching mechanisms of low mass galaxies in the local universe? Because we do see some quenched or lots of quenched low mass galaxies in the local universe. So if they cannot quench themselves, and who did that? So what was the quenching mechanism for low mass galaxies? And this topic became more and more interesting when people find more and more quenched low mass galaxies in early universe. For example, here is a result from a quenched galaxy at redshift 7 found by JWST's JACE survey. Okay, star formation history shows this is a single burst with a duration of about 30 million years, match the duration of low redshift, low mass galaxies. And then star formation rate got stopped. What happened after that? If we can observe these galaxies for next 20 or 100 million years. Is that quenched forever, or is it just a temporary quenching at redshift 7? So to understand that, we perhaps have to move again back to low redshift to understand the quenching mechanisms of low redshift galaxies. If galaxies were not able to quench themselves, so maybe the primary quenching mechanism is related to their environment. So many studies point to this conclusion. For example, Gihao et al., they showed if you look at the quenching fraction, how many galaxies are quenched, as a function of the distance to massive host galaxies. And when you go beyond 1 or 2 MPCs away from massive host galaxies, low mass galaxies here, yellow and green and blue, almost all of them, filled galaxies, are star forming. And you can only find quenched galaxies quite close to massive host galaxies. And question is, can we see a similar result at higher redshifts? By using HST data, candles data, we actually see similar results at redshift 1. But are we able to see similar results at even higher redshifts? At that time, we need a larger sample. And this is, again, where Roman can help us. So also, the quenching time scale is very important for us to understand the physical mechanism. Here, I'm going to give you an example of how to understand the quenching time scale, or how to measure quenching time scale indirectly. So here is a plot showing you specific star formation rate versus the central mass density, projected central mass density, basically the mass density over 1 kpc from the center of galaxies. And the different panels shows you different redshift. This is a low redshift, and this is a little bit high redshift. And from left to right, we have different stellar masses. Okay, so if you look at high mass galaxies, and this is a very famous, well-known L shape or elbow shape. So if a galaxy is star forming, they have this is a star forming galaxy, so black. They have a low central mass density, low sigma 1. And when they reach a high central mass density, red galaxy here, they become quenched. So that means central mass density has something to do with the quenching. For massive galaxies, we believe that's because of the activity of AGN, AGN feedback. Interestingly, we also found a similar result for low mass galaxies. Here, they also show this similar elbow shape in specific star formation rate versus central mass density plot. Okay, well, you can see, okay, maybe that gives us implication that there are supermassive black hole or central AGN also quenching low mass galaxies. Well, I don't want to go that far. I still want to go back to the conclusion of environmental quenching. So how can we understand this elbow shape for low mass galaxies as well? So we have a simple model. If you pick up a star forming galaxy and study its mass profile, central mass density and outskirts mass density, we have the observation. And we know after the quenching, so this blue profile would be changed to the red. Okay, we can measure the mass profile before and after the quenching. Now, if we also get specific star formation rate profile as a function of a radius, so this is what happened during the quenching, and then we can calculate, okay, to go from blue to red, throw in the rate of green, how long does it take for a sample of low mass galaxies? Okay. And that time is what we call the time scale of quenching. And we got a very long time scale, about 4 billion years. Okay. So this long time scale tells us low mass galaxies, they gradually quench them outside in, first from outskirts, but they keep their central star formation. And the possible mechanisms could be starvation, which basically means cut down the gas supply by environment, and plus not all, but plus overconsumption by using up all the residual gas in the center. So that means any quick quenching time mechanism, for example, run pressure stripping, they are unlikely to be the reason of quenching. And also quenching mechanisms that have to change the morphology of galaxies during the quenching. Okay, so I think my time is running up. So let me quickly say a few things about the ROMAM, because this is a ROMAM conference. So what ROMAM can do, or what we can use ROMAM to do for low mass intermediate redshift galaxies. So we can get a very complete sample to low stellar mass, and we can study better the environmental effects. For example, I can repeat all the analysis I did for candles, now divided my sample into galaxies at different environments, filament, center of cluster, outskirts of cluster, or field, and to see whether the center or the mass profile change not only with quenching but also with environment. And also, large field of view of Raman can help us to catch those shorter time scale phases, for example, the peak of a starburst, so we can know better the time scale of a starburst. And if we have some field quenched galaxy, we can also study them to know whether AGN feedback is also playing a role in low mass galaxies. But there are a few challenges I also want to mention. First is the limited number of filters Raman has. Of course, if we combine Raman with other telescopes, for example, LSST, we got a better wavelength coverage. But we still lose the infrared part, so that's why when I heard Aaron said on Monday that there's a possibility to add a K-band in Raman, I'm very excited about that. Also, the sensitivity. So if I use a reference Grisma emission line flux of 10 to minus 16 erg per second per centimeter square, so that turns into different star formation rate caught as a red line shows here. Basically, you can see they cross the star forming main sequence, which is green line, way before we reach the mass completeness. So that means those galaxies here, if we keep 10 to minus 16, we were not able to get emission line measurement. So we really need to push it, the emission line limiter down to even lower flux. Okay, so I'm running out of time. Here's my take-home message. I'm going to leave it here. The important thing I want to mention is to echo Aaron's question on Monday. So if we cannot get all of the depths, number of filters and areas, what do I prefer? I actually prefer much deeper observation with a little bit more number of filters. Thank you.
Thank you, Yicheng. It was a very nice talk. So we'll take time for maybe one question before moving on to Kyle. Christy.
Thanks, Joe. Topic near and dear to my heart. I'm curious, given the systematics in especially IMF and stochastically populating the upper end of the IMF and such, but H alpha and UV star formation rates, and how that maps to the durations. Have you thought about comparing to burst durations that have been measured from CMD fitting with more, with higher temporal resolution that can constrain that better without as many systematics?
So, so you are talking about basically replace the FUV star formation rate through SED fitting star formation rate, where you have a better control of.
Yeah, I mean you can't do that technique at 0.5 or redshift of 1, but I mean as a comparison sample, because it looks like you're interested in comparing to what's at Z of 0 for burst durations and amplitude and strength, and there's a lot of constraints from Z of 0 that don't just do integrated light measurements, but from individual stars and being able to do more temporally resolved star formation rates for comparison with just greater granularity.
Yeah, that's a good point. So we haven't done that, but that's definitely something we can do in the future. And also just back to high redshift, we are actually also interested in answer this question because bursty or not is just the first step. And how bursty they are, that's something we want to compare to the model to see whether they can really provide enough momentum or energy to solve the cost band core problem. But yes, that's a good point. Thank you.